When most people think of Cold War engineering, they imagine concrete bunkers, hidden missile silos, or secret communication networks. Rarely does anyone stop to consider something as seemingly mundane as wooden support beams. Yet these beams were often the backbone of critical facilities, from underground command centres to safe storage warehouses. Water infiltration posed a serious risk. If left unchecked, it could compromise structural integrity, ruin sensitive equipment, and turn a classified installation into a liability overnight. The way engineers tackled this problem reveals a mix of ingenuity, resourcefulness, and methods that still have practical applications today. Cold War engineers approached water damage with meticulous prevention rather than last-minute fixes. During the height of the Cold War, secrecy and operational readiness were paramount. Engineers knew that even minor water damage could cascade into catastrophic failure. Their first strategy was prevention. Wooden beams were not simply installed and left to weather conditions. They were carefully selected for durability, often using species naturally resistant to rot, like oak or Douglas fir. Beyond species selection, wood was treated with chemical preservatives before installation. Creosote, borat compounds, and oil-based treatments were common, forming a protective barrier that penetrated the wood and repelled moisture. Installation techniques were equally strategic. Engineers designed drainage paths and ventilation systems that encouraged airflow around wooden structures. Beams were elevated slightly above damp floors and separated from concrete foundations with moisture-resistant membranes. Every joint was sealed, and critical connection points were reinforced with metals resistant to corrosion. The goal was simple: eliminate any standing water, reduce humidity exposure, and allow the wood to breathe without becoming saturated. Even with prevention, water sometimes found its way in, through leaky roofs, condensation, or accidental flooding. Cold War engineers had a layered response. First came inspection and assessment. Every beam was carefully probed for softness, warping, or fungal growth. Areas that showed early signs of damage were dried using forced air or low-heat systems that prevented rapid expansion and cracking. In some underground facilities, specialized dehumidifiers operated continuously to maintain relative humidity levels under 50%. A level at which most rot organisms struggle to survive. For beams already compromised, chemical stabilization was the next step. Engineers applied solutions that penetrated deep into the wood fibers. Borax-based liquids, often mixed with solvents, were brushed or injected under pressure. This not only halted fungal activity, but also reinforced the structural integrity by binding weakened fibers together. In extreme cases, small sections of beams were replaced or reinforced with steel plates and epoxy resins, creating hybrid structures that preserved load-bearing capacity without full reconstruction. The strategies developed by Cold War engineers are, surprisingly applicable today, both in historical preservation and survivalist construction. If you are restoring an old wooden building or bunker, selecting rot-resistant wood species remains the first and most critical step. Applying a deep, penetrating preservative can, dramatically extend the life of beams, especially in high-humidity environments. Proper installation still matters. Elevate wood from moisture. Prone surfaces create airflow and use moisture barriers wherever possible. For existing structures suffering water damage, begin with a careful assessment rather than rushing into replacement. Dry slowly using controlled airflow, avoid high heat that can crack the wood, and stabilize compromised areas with borate treatments or epoxy injections. For those interested in DIY survival shelters or underground bunkers, these Cold War techniques provide a roadmap for durable construction without relying solely on concrete or steel. Understanding how wood interacts with water and humidity can, honestly, prevent failures that might otherwise go unnoticed until it is too late. Beyond practical application, studying these engineering methods gives insight into the mindset of Cold War designers. Every beam, every chemical treatment, and every installation technique was chosen to maximize resilience under extreme operational pressures. This is a level of forethought rarely applied outside critical military infrastructure. By examining their work, historians and survivalists alike can gain a deeper appreciation for the ingenuity required to maintain secrecy, security, and safety in high-stakes environments. Whether you are restoring a historical site, building a secure shelter, or simply curious about the technical solutions of the past, Cold War engineering offers lessons that remain relevant. It shows that even in the face of a constant threat, be it water, decay, or enemy sabotage, systematic science-based approaches can preserve structures far beyond their expected lifespan. If you are passionate about uncovering these hidden histories and applying practical knowledge from the past, subscribe to In the Beginning and share this with fellow history enthusiasts. Understanding the past isn't just about stories. It's about learning strategies that can still protect and preserve today.